My name is Jan Mueller with the Environmental Energy Study Institute, and I'd like to welcome you all to our briefing today on natural gas as a transportation fuel. We don't have the benefit of a podium, but given the room and that situation, we'll have the opportunity to have an intimate discussion about a very important topic, or at least a technology that can play a big role in some things that we all care about: energy security, economy, environmental impacts, etc. So for those of you who don't know us, the Environmental Energy Study Institute was started about 25 years ago by members of Congress in both parties, in both chambers, to provide independent, authoritative information on environment and energy issues. And so for 25 years, through education, outreach, partnerships, some of you, including the people in this room, and constructive dialogue, including our briefings here on the Hill, we try to advance solutions that make sense. And as I said, to do that, we take a broad view about what the environmental impacts, the economic impacts, energy security, public health, again, everything that we care about. So we've been doing, we do work on all aspects of energy issues. I myself am leading the work on transportation, not just transportation fuels, but other transportation strategies and policies that can reduce our energy dependence, reduce our greenhouse gas emissions, improve and sustain our economy. So we've been doing, if you look at our website, esi.org, you'll see we've been doing a number of briefings on transportation fuels, and this is sort of the latest iteration. We try to look at each transportation fuel option through a similar lens, but each fuel has its own idiosyncrasies, if you will. And natural gas, which we're really pleased to be talking about today, is, we all know it as a fuel. I think we've all seen buses here on Washington, D.C. streets. I'm a bike commuter myself, and I appreciate natural gas buses as much as anybody. But today's, we're going to look at some of the maybe things that people might not think about. I think issues that are not necessarily part of the common discussion. So I think we are being technology neutral. We're just trying to look at what the issues are. We don't have a position on vehicles, but we're trying to ask some hard questions. So that's a little qualifier as far as what you're going to hear today. And we very much look forward to the discussion about what the role of natural gas vehicles will be in our energy future. And I think the one place that we start is at the status quo with a transportation sector that's powered by 95% or more by oil, most of which is imported, is not where we want to be. So we have a great panel, and without further ado, I'd like to introduce, let me just walk through the overview of the presentation. We have Callie Johnson from the National Renewable Energy Laboratory, who's going to give us sort of a broad view of the state of the market for natural gas vehicles, where the opportunities are, where the challenges are. We have Dr. Daniel Cohn from the Massachusetts Institute of Technology, where he's done a lot of research on different transportation technologies, but he was also the executive director of the Future of Natural Gas study that MIT did, and they obviously looked real hard at transportation, natural gas as a transportation fuel. We're pleased to have Dana Ongst, the chief of water standards and facility regulation with the Pennsylvania Department of Environmental Protection. When we're talking about natural gas as a supply, we have to look at the whole supply chain. So we are going to try and address, understanding that this is a big issue, and we could have briefings on each one of these pieces, but we are going to look at the supply side and what the environmental concerns are on the ground, and I think the Pennsylvania perspective will be very interesting. We're also pleased to have Lynn Pittenger, consulting engineer who does a lot of work on unconventional, especially shale gas evaluations, and so what the real prospects and challenges are for meeting our long-term natural gas supply. And finally, we'll have Stephen Hamburg, chief scientist for the Environmental Defense Fund, who has a broad background on climate and energy issues, but is going to be looking in particular at some of the greenhouse gas implications. So without further ado, Callie, who has a master's in environmental management from Yale, where he specialized in energy economics. He's been with the EPA Climate Protection Division before NREL. But his work at NREL is very much focused on the Clean Cities program, trying to look at the applicability of different transportation technologies in different markets and what makes sense, as I said. So without, please, Callie, start us off.
Thanks a lot, Jan. Let me get my slides up. All right, thanks. I'm going to be talking about natural gas vehicles and their required fueling infrastructure and some of the economics of, of natural gas projects today. But first, I'd like to start with a 30,000-foot view and just ask the question, why use natural gas vehicles? There's a lot of companies and individuals using them, and that goes a long way to answering the question, why are we here right now? Why is there a big interest in natural gas vehicles? One is the economics, which I'll spend a majority of my presentation on. I'll look at the fuel prices, the vehicle attributes, the vehicle industry, the infrastructure. Another major advantage of natural gas vehicles is the increased energy security. Natural gas is 98% from U.S. and Canada, and right now with gasoline and diesel prices skyrocketing because of geopolitical events is a particularly timely time to be having this discussion. Another benefit of natural gas in vehicles is that if you look at the full life cycle of natural gas, it uses hardly any petroleum, which a lot of other alternative fuels use varying amounts of petroleum to extract or grow and transport. So that's another major advantage of natural gas in vehicles. It also reduces local air pollution and greenhouse gas emissions, which I will talk about in upcoming slides. The primary driver for why companies, mostly fleets, would want to be using natural gas is because of the difference between the diesel or gasoline cost and the CNG cost. There you can, all natural gas projects require an upfront investment that needs to be paid off with that fuel savings. And as you can see, that fuel savings is consistent and it's been growing over the years, and EIA projects that difference to be growing more. So the per GGE, which is gasoline gallon equivalent, difference between natural gas and the petroleum fuels is projected to grow in the future, and the savings will increase. Another major advantage of natural gas in vehicles is its consistency. You can see those top two lines are gasoline and diesel, very volatile. As a matter of fact, right now, we're up above $3.50 for gasoline and up around $4 per gallon for diesel, which would even accentuate that volatility even more. And so that is a major hurdle for businesses to plan this unpredictable cost, because most of the fleets and companies in the transport business, this is their main cost, and that unpredictability makes it very tough to plan for operations. And to understand the economics of natural gas vehicles, let's first look at the way the industry is configured. It's very unique. It's different than all other vehicle industries in that we have three major players. There's the original equipment manufacturers. The top two produce heavy-duty engines, and Honda produces a Civic that are dedicated to natural gas. And then you have conversion kit manufacturers that made kits so you can convert gasoline engines to use natural gas. And these kits require upfitters to put the kit on various vehicles. Two of these conversion kit manufacturers make bi-fueled vehicles that can use both gasoline and compressed natural gas. And each kit engine combination, whenever you put one of these kits on a specific engine, it requires a certificate of conformity from the Environmental Protection Agency that basically says that it meets emission standards, but that also kind of limits the number of vehicles being offered as a CNG version. And then there were a couple of other heavy-duty manufacturers that dropped out in the early 2000s. Detroit Diesel and John Deere made one. But the Department of Energy and some of the California agencies are working with OEMs to produce new heavy-duty natural gas engines. So now let's look at what drives the cost for natural gas vehicles. It's two main things. It's the size of the vehicle and the range that it needs to travel. The size makes a major difference because the smaller vehicles traditionally use gasoline engines, and it's simpler and cheaper to convert a gasoline engine over to compressed natural gas because it's spark ignition, and you have a lot of the same attributes and components of the engines. The large heavy-duty engines normally run on diesel, which is compression ignition, and so changing from compression to a spark ignition requires more changes and more engineering, which increases the cost. And then if we look at range, generally the longer the range is for the vehicle, the further it needs to drive. You need more tanks and more storage capacity for natural gas on the vehicles. So as you go from the commuting sedan, which generally needs less than 250 miles, like the Honda Civic, up through the medium and heavy-duty vehicles, which range from 250 to 400 miles, up to the 18-wheelers, which need over 500 miles of range. You increase the required storage capacity, and with liquefied natural gas being at the far end of the spectrum, liquefied natural gas just helps people fit more energy into a small container, essentially. And so, as you can see, as you increase the size and range, you increase the cost from like $7,000 for the Civic. That's an incremental cost, meaning that the compressed natural gas version costs $7,000 more than the gasoline version, on up to around $50,000 for the heavy-duty vehicles. This is a bit difficult to see, but I just put a map of the compressed natural gas infrastructure out there. They have 870 stations, and most of them have a fleet based around them, so they can be kind of self-sustaining, and then they're starting to cluster together, so fleets can go from one station to another, and they're starting to form various corridors, like you can see in California and up in the New York area. And then to look at the LNG infrastructure, it's not as well developed yet. It's a bit in earlier stages of development, and you can see there's a couple of major clusters in Los Angeles, and then going up to San Francisco, and then going west to Las Vegas. And there's various ones throughout the East and Midwest, which many of them tend to be around 500 miles from each other. So you can see they're kind of starting to work in collaboration, where they can run a heavy-duty truck from one city to the next, make it the whole way, refuel in that city, and then go back. Now, as far as the refueling infrastructure goes, the major cost drivers are based on how many compressors you need. That's the most expensive part of the refueling infrastructure. And so your compression requirements are driven by two things. One of them is how much fuel are you running through the station on a regular basis, and then the other one is how quickly you need that fuel to be pushed out. So because if you need a lot of fuel but not very quickly, you can compress and then store it, and you'll have it available as the vehicles come in. But if you need it really quickly, you need a lot of compression capacity, which is very expensive to go right away. And so these top two rows in the table kind of dictate how much fuel gets pumped through the station. And so that's the number of vehicles refueling at the same station, and then the amount of fuel per vehicle. And then the next two, the required fueling speed and the break between vehicles, kind of dictate how quickly you need to have that compressed natural gas available. And so basically the quicker a vehicle needs to refuel, like if they're in a fleet that just doesn't have much time, they have to get in and out really quick, that makes it more expensive. And then if you have no breaks between the vehicles, such as if you have an entire fleet coming in, say after a day of transporting people in in a transportation bus, then you have to refuel many vehicles quickly, and it becomes more expensive. And so if you kind of sum up the past couple of slides and look for what fleets are particularly favorable to use natural gas, we start by looking at that annual fuel use, because remember that you're paying off the upfront infrastructure costs by fuel savings, by the amount that natural gas is cheaper than diesel. And so therefore the more fuel that a vehicle uses, the quicker it'll be able to pay off its infrastructure and the more profitable it will be. So you can see that these vehicle types are listed from the ones that use the most fuel to the least. And then if you have the range determines how many, basically it determines how much fuel you need to put on the vehicle at once. If it has a long range, you need to put a lot of fuel through the vehicle, whereas if it has a short range, you can just kind of put smaller amounts, and so you don't have near the capacity for the station. And then you want to look at the available refueling time. If they're a fleet that all comes into the station at once, it has a long refuel, or it has a short refueling time, which makes the stations more expensive. And so then so those two columns kind of dictate what equipment you're looking at. And so you can see for the combo truck, you probably need liquefied natural gas, which is more expensive. For these next four, you're fine with a fast CNG station. Then when you get down into like the school buses, which have a long down period, you can use a slow CNG station, which is a lot less expensive and more cost effective. And then if you wrap all of the economics, including maintenance and operation, together, and look at the overall cash flow of the project, this is how the payback period, which is the number of years it takes to get your investment back, it's how it is determined by the price of diesel. So if you assume that compressed natural gas, or natural gas in general, stays at about the same price, this is the change that the price of diesel will have on the payback period. As you can see, we're up at, I think, $3.90 per gallon right now for diesel, and so that would put us at about a 3-year payback period. And it's just interesting to see how the different prices of diesel will affect that payback period. And these are two different fleets. One of them is the transit buses that have a slightly longer payback period, and then the trash trucks, which have a slightly lower payback period. And each one has two different sizes of fleets. All right, and this is how the various tax credits that were in place in 2010 affect the payback period. You can see that the fuel tax credit, whoops, I just forwarded, the fuel tax credit and the vehicle tax credit make the biggest difference. Taking that away really increases the payback period. And then the station tax credit that was $50,000 or 50% at the time has less of an influence. And I also want to point out that there's synergies between the three credits. If you add up the differences between the all credit scenario and the other credit scenarios, it doesn't quite add up to the no credit scenarios. And for air pollution benefits of natural gas, In the light-duty vehicles, we have this chart that was done by Argonne National Lab that shows that on average, by combining multiple studies, you reduce VOCs by 10% from gasoline, carbon monoxide 20 to 40%, nitrogen oxides stay about the same, and particulate matter goes down 80%. And then methane is quite an increase because natural gas is methane. And then if you look at the emissions reductions in heavy-duty vehicles, it's less clear because there's so many different scenarios, so many different vehicles, and the diesel vehicle, which is the baseline, has been changing quickly to meet 2007 and 2010 emission standards. But NREL has partnered with the University of West Virginia to do a number of studies on different fleets, and there's a nice summary at that website. It does show that in most of the fleets, there have been very substantial reductions in the criteria pollutants. And then just as the diesel vehicles have been striving and going to great lengths to meet the 2010 emissions standards, Cummins Westport had an engine that had already met the 2010 emissions standards back in 2007. But we need more studies comparing the various fleets' emissions with the diesel emissions as we come closer to the 2010. Here's as far as greenhouse gas emissions go. I like the California Air Resources Board has done a pretty good analysis of the life cycle greenhouse gas emissions for their low carbon fuel standards, and you can see that compressed natural gas reduces emissions 21% below low sulfur diesel. LNG doesn't do quite as well on their rating, which is partially because they assume a 10% efficiency reduction, which I'm not necessarily in agreement with. But then there is an 86% reduction if you look at landfill natural gas. And here's for the light-duty vehicles. You have a 29% reduction in greenhouse gas emissions. For CNG, 88% for landfill CNG. And the last thing I want to mention is the renewable natural gas, which is also called biomethane or biogas. It comes primarily from landfills, from livestock operations, and from wastewater treatment plants. The vast majority of it is used for electricity generation right now, and an advantage of this source of energy is that they're well dispersed throughout the nation, and we have the technology right now to clean it up to be able to use it in vehicles. And I will wrap it up with that.
It's a great way to start us off, and Dan, why don't you just take it from there? Actually, I should give me 30 seconds. Obviously, there's a lot of, like I said, Dan has been involved in a lot of work at, he's actually the head of the Plasma Technology Division in the Plasma Science and Fusion Center at MIT, and has been involved in hydrogen technology and holds a whole bunch of different patents on plasma, and I can't claim to understand all that, but just really interested in what the study found. Thank you.
Well, thank you. Appreciate the opportunity to participate in this. This briefing. I'm going to be summarizing the work we did as part of the MIT study on the future of natural gas. We issued a interim report in June of 2010, and we expect to issue our final report in June of this year. Now, the aspect of natural gas for transportation that I would like to cover has to do with the prospects for achieving security and environmental benefits. In our study, we considered both the direct and indirect use of natural gas for transportation. So we considered CNG and LNG, of course, and then we also looked at conversion into liquid fuels, and particularly methanol. And in our study, we placed a special emphasis on the requirements for economic attractiveness of use of natural gas as a transportation fuel. Callie's talked about the economic issues involved in determining where CNG is promising as a transportation fuel. As he mentioned, you have to weigh the fuel cost savings versus the incremental cost of the vehicle relative to gasoline or diesel engine vehicles. And our view was based on previous purchasing and use trends that in general you would want a payback time of around 3 years for most buyers to purchase a alternative fuel vehicle. So given that frame of reference, we made an assessment of the potential impact with particular emphasis on the near term, and by near term I mean the next couple of decades. And our conclusion is very similar to what you heard earlier. The greatest potential is for high mileage per year vehicle market segments because there the fuel savings is sufficient to pay back for the higher incremental cost. The most favorable segment from our point of view was short-range heavy-duty vehicles, and then after that high-mileage light-duty vehicles, generally fleet vehicles. We made an estimate of the potential impact that these market segments could have on security and greenhouse gas goals, assuming 100% penetration. So assuming that you could get 100% penetration of these market segments, we concluded that you could replace a little over 1 million barrels of oil a day, which is equivalent to using around 2.5 TCF per year of natural gas. The greenhouse gas impact would be to reduce the CO2 emissions from vehicles by around 2%. That's assuming a 25% CO2 reduction. That's assuming the same engine efficiency for a natural gas vehicle as a gasoline vehicle. This reduction would be somewhat greater if you took into account the higher efficiency that natural gas can provide with the correct engine technology. Now, there is another factor that needs to be taken into account, and that's the methane emissions from the production, processing, transmission, and use of natural gas. And the EPA has recently increased its estimate of methane emissions from natural gas systems. And when you take that into account from a systems point of view, it can have a significant impact on the greenhouse gas benefits from all natural gas-based fuels. So in this case, the greenhouse gas benefit would be less than 2%. Now, what about LNG for long-haul trucks? LNG has the advantage, as Callie mentioned, of having a high energy density and is thus suitable for long-haul applications. It does face a number of challenges. One is the high incremental cost. Even with short payback time, high incremental cost can be a concern for purchasers of trucks. There's also the challenge of the operational limitations of using a super cold fuel. This fuel is at minus 162 degrees C. It has to be stored in a special thermos bottle, and you can only keep it at the cold temperature for a limited period of time. It has to be used in less than a week. And there is concern about the predictability of the thermal containment of the fuel. Another challenge is the infrastructure requirement. It's expensive, and the potential users, the American Trucking Association, have expressed concern as to whether you would have a competitive fueling structure for their truckers if the trucks were to be used on the highway and have to use filling stations on highways. So this assurance of price competition between fuel suppliers is a practical consideration of some significance. Another challenge is the possibility of a reduced resale value for LNG trucks, because a significant number of long-haul trucks are sold internationally after they're used. And then the question arises, what would be their resale value if the country to which they're sold does not have an LNG infrastructure? Now, these challenges that I mentioned can be mitigated if the LNG trucks are used for long-haul applications between hubs. There, the refueling would be done by the facilities owned by the companies, and the drivers would have certainty as to what the fueling availability is. The trucks can be used in a very predictable way, and so this looks to have significantly more potential than on-highway use. And this could be a modest but significant market. And again, just to get a frame of reference, assuming 100% penetration of this market segment, oil consumption could be reduced by around 0.4 million barrels a day, corresponding to the use of 0.8 TCF per year of natural gas. It's difficult to estimate the greenhouse gas emission benefit because it depends very much on the efficiency that's assumed for liquefaction. But a representative number is on the order of 10 to 15% greenhouse gas reduction per truck. Now, this, again, does not include the methane emissions from natural gas production, processing, transmission, and distribution. And this, as I mentioned earlier, this number has gone up, and so this can have a significant impact on the degree of greenhouse gas reductions. Now let me turn to conversion of natural gas into a liquid fuel. And there's significant motivation for this. If you could convert natural gas into an economically attractive liquid fuel that you could use like gasoline or diesel, your barriers provided by high incremental cost and the need for a completely new infrastructure would be removed. Natural gas conversion into liquid fuels has been done for a long time. The uses, though, have not been for transportation. It's been mainly for chemical production. And the way it works is the natural gas, it goes into a unit called a reformer. It produces what's called a synthesis gas, which is hydrogen and CO. That synthesis gas is converted by a catalyst to various types of liquid fuels. And you have a wide range of fuels you can produce, going all the way from diesel to ethanol, mixed alcohols, and then the smallest molecule you can produce is methanol. And methanol itself can be used as a feedstock for producing gasoline and DME, dimethyl ether, which is a clean-burning fuel for diesel vehicles. Now, of all these liquid fuels, methanol is the fuel that's best established. It's made in large quantities. The 13 billion gallons are produced per year. It's used for the chemical industry. And it's the one that's made most efficiently. It's about 67% efficient in its conversion. Now, if you were to take the natural gas in the U.S. and deploy the current technology, it would be possible to produce methanol at a cost of around $1.30 per gasoline gallon equivalent. That's taking natural gas at $4 per million BTU. So that's essentially $1 per gallon less than gasoline on an energy basis. And even if the natural gas price were to go up to $6 a million BTU, methanol could be produced at a significantly lower cost than gasoline is produced now. Gasoline right now is produced at a cost of around $2.30 per gasoline gallon equivalent. So this is a very important aspect, that it's possible to produce a liquid fuel that could replace gasoline and diesel that actually costs less. Now, there are two ways that methanol can be used. One is in light-duty vehicles, in flex fuel vehicles, which are similar to the ethanol gasoline flex fuel vehicles we have now, which there are around 6 million on the road in the U.S. The additional cost to a vehicle that has the ethanol gasoline capability would be on the order of $100 to $200. So the incremental cost would be minimal, and in addition, the driver would potentially have a fuel cost saving. Now, there is legislation being considered to mandate that light-duty vehicles be capable of operating on ethanol, methanol, and gasoline. The other option is a heavy-duty vehicle, where the vehicle could be operated on methanol and gasoline mixtures, flex fuel, and there would be two economic benefits. One is the vehicle cost would in fact be lower than diesel, not higher, and the reason is that these vehicles would use spark ignition engines, which have low-cost exhaust treatment systems and low-cost fuel injectors. So there could be a $10,000 to $15,000 saving, and there could also be a lower fuel cost saving. So there's significant potential economic benefit. There are barriers, the risk in building natural gas to methanol plants. Another barrier is there are not too many people who like this fuel. The gasoline and automobile companies are not enthusiastic about it, and concerns have been raised about health and environmental effects. So to sum up, our conclusion is the main benefit from natural gas-based fuels is improved energy security, not a greenhouse gas benefit. There's a modest potential impact of CNG and LNG in terms of reducing our oil use, and this impact is limited by economic and operational issues. With regard to methanol, there is a large potential energy security impact because of its favorable economics and readiness for deployment. However, as I mentioned, there are significant barriers to its deployment. Thank you.
Thank you very much, Dan. And we're going to switch gears a little bit, but we're going to come back to all these issues both in our panel discussion and when we get to Stephen. And Dana Ongst from the Pennsylvania Department of Environmental Protection got slipped in just before we started, so I didn't get to plug him for his bio information, but he's held a couple of different titles because we've changed it a few times on the program, and I guess now you're actually the acting director of DEP. So why don't you maybe provide us a little background and talk about something that a lot of people that's gotten a lot of hype, water resource issues and shale gas development and fracking and whatnot. And I was really fortunate to find Dana, and really thank you for coming down to try and shed a little light on what's been a very emotional issue for some folks. Thank you.
Thanks very much, Jan. Yes, I on Monday started a new gig, so I am currently the Acting Deputy Secretary for Field Operations for Department of Environmental Protection in Pennsylvania. Field Operations is essentially what it says. It's out and doing all programs in the field offices, so I'm having to get up to speed very quickly. But as most of you probably are aware, one of the big potential opportunities for new natural gas development in the country is shale gas, and we'll hear more on more detail on that next. But one of the challenges that it poses to Pennsylvania is we have what's called the Marcellus Shale Formation that underlays about 2/3 of our state. It is a huge economic opportunity, as you may imagine, for the Commonwealth, because most of this geologic formation underlies areas that have been, over the last 25 to 30 years, hit particularly hard by the move to the Sun Belt and are otherwise known as the Rust Belt. So a lot of these older towns and cities in north central, northwest, and southwestern Pennsylvania see this as a very, very huge opportunity, as does the Commonwealth as a whole. At the same time, the development of this play brings with it some very, very seated and long-standing worry over legacy. and that is because of the prior industry, energy extraction industry, that's left its mark in Pennsylvania and these same areas for the most part, and that being the coal industry. So I think we are second, if not first, in the state, a number of streams with acid mine drainage impairment. Are second in the country as a state with the most miles of streams with acid mine drainage impairment. So we had to get out ahead of this. And when we first became aware that this was going to be such a huge place, a huge economic opportunity, the first thing we had to do was find out how many areas of environmental protection that this whole operation, the development of these wells and the development of the infrastructure necessary to deliver the gas to market, was going to affect. And this gives you an idea here of all of the areas in our view of environmental protection that we currently interact with regard to this play. And I'll go through each one of these. First, water sources. Each one of these wells, when they're drilled and hydraulically fractured, and because of the technique, the depth, and the horizontal drilling, can take up to 5 million gallons of water to hydraulically fracture. Generally, we're told it varies from 3 million to 5 million, but it can be up to 5 million. And when the industry first moved into Pennsylvania, we are a very water-rich state. We have the second most miles of streams of any state in the country, Alaska being first. 86,000 miles of streams in Pennsylvania. It was looked at as an abundant source, and we were never going to have to worry about the quantity available. Unfortunately, they came into Pennsylvania in the springtime when the snow melts and it rains, and so the streams that they saw flowing very healthily in the summertime don't always flow that way. So we ran into issues with the available water, and we had to get on top of that issue. Much of the water, when it's used in a hydraulic fracturing operation, is what we call consumptively lost, meaning that it is contaminated to a point where it's going to have to be disposed. And in a lot of cases, the common practice was deep well underground injection control wells. So it's consumptively lost. How much water will be needed? We need to get projections of that because we need to figure out whether or not we have that available flow in our streams and our lakes, and that means how much water is available. The good news is we're starting to get data back after a couple of years of being in this business, and we're finding out in the Susquehanna River Basin, which has a separate federal compact, the Susquehanna River Basin Commission, that oversees water consumptive loss. We're finding out that the daily consumption is no greater than one of our power plants that essentially evaporates, steam electric station that evaporates through cooling towers. So on the grand scheme, what we're finding is it's not as big of an issue as it may originally have been thought. But again, we've only been at this a couple of years, and the industry has not completely ramped up at this point. So water sources was an issue. Site development. These pads where they construct the wells, and generally they'll construct a pad, a good-sized pad, maybe 6 to 8 acres, and then they'll drill multiple wells off these pads. So we have these well pads being constructed in the northern part of the state, the north-central, northwestern part of the state that are primarily forest, or even a lot in agriculture as well. So we have concerns about the erosion and sediment coming off these construction sites, and then post-construction stormwater. What type of post-construction site characteristics are going to be left on the landscape, and are you increasing stormwater runoff, thereby increasing erosion in your streams as well? So we also had to consider the protection of our waterways and our wetlands. A lot of wetlands, given you might assume the number of streams that we have, and we don't want construction on these well sites impacting or destroying wetlands. So that's another big issue that we had to get our hands around. And then finally, protection of the water quality. Construction of roads and pipeline facilities and the well pads themselves, the wells themselves, has the potential to impact the stream, again, in terms of erosion and sediment. But we have stream crossings where the roads have to cross streams, pipes have to cross streams. So we're very concerned about that. So site development issues were also a big concern for us. Well construction and completion. And what we consider completion includes what everyone knows as hydraulic fracturing, or for short, fracking. So in constructing the well, we have to make sure that we have proper regulation in place requiring well casing that meets certain standards to prevent gas migration. One of the issues we're chasing right now in some areas is Pennsylvania's been a oil and gas state for 135 years plus. The first oil well in the country was outside of Oil City near Titusville. We've had natural gas in our infrastructure, our energy infrastructure, for many years. We have naturally occurring natural gas in shallow formations, and a lot of times when these wells get started, they hit these shallow pockets, if that's what you want to call them, unknowingly, and we end up with a gas migration. So proper drilling, construction, casing requirements needed to be developed, and we recently enacted new regulations in that area. A lot of these activities involve the construction of dams or large impoundments, because what the industry has gone to now over the concern with the amount of available water is recycle and reuse a lot of the water. They've figured out a way to recycle and reuse so they don't have to use as much fresh water. But that involves construction of large impoundments where they manage these flows. Fresh water in, hydraulic flowback water in to mix for another frac job on the same well pad for a different well. So we had to get our arms around the construction of dams and impoundments, meaning we can't just dig a hole and put water in it, because if it's okay for fresh water, but if you put flowback water in there and it's not a lined impoundment, then we have an issue with groundwater. So that's another issue we had to address. And then finally, site restoration, and this gets back to post-construction stormwater, but it also gets back to issues related to deforestation, and I'll get into that a little bit later. These slides get a little busy because I tried to get as many on here as I could. Wastewater. Many folks have probably heard that, to no surprise to those of us who've been dealing with this, and I don't want to make it sound like we're all knowing, but there are naturally occurring radioactive materials in this formation. This formation has a certain degree, a small percentage of uranium, and uranium obviously decays into other materials, and that's considered naturally occurring radioactive material, or NORM. So the wastewater, when it comes back out of the wells after the well's been fractured, can pick up quantities of this NORM. It can, at certain levels, present some health concerns, especially if it's subsequently concentrated through a treatment process, where this material is actually treated, the solids are dropped out. That can concentrate some of this NORM, and that's called T-NORM, technically enhanced naturally occurring radioactive material. But nonetheless, it's naturally occurring. And we have identified the types of NORM in this wastewater. We've done pretty extensive sampling on our own, and the industry has also provided us with a lot of data that has given us an idea what's in the wastewater and what levels these parameters are present. We've determined right now there's no immediate hazard at these levels, but we're going to take precautionary controls. We're going to get out ahead of this. We're going to require monitoring of the wastewater. We're going to also accelerate the frequency at which downstream drinking water intakes may have to monitor their water, just to make sure, to be on the safe side, that what we're seeing now continues to be seen into the future. The other parameter in the wastewater is the total dissolved solids, and these can run very high. And again, this formation, being a shale, is an old seabed, so it's essentially loaded with salts. So when you fracture this material and you put water in there to fracture it, it comes back as very, very strong salt water. So there are problems with the TDS. They are a drinking water contaminant, albeit for what's considered secondary effects, meaning taste and odor, and they may discolor laundry or prevent your dishes from getting clean. But it can also cause high TDS can also cause other operational problems at drinking water systems, such as the formation of disinfection byproducts, which some are known to be carcinogens, so we have to keep an eye on the TDS. And then finally, it can cause toxicity to aquatic life in streams if the TDS isn't managed properly. We did an analysis that showed that our rivers and streams had a very limited capacity to take additional TDS. There are a lot of legacy loads of TDS in our streams. Many of our streams are affected by it, so we had to get out ahead of that issue as well. There was a growing demand for the capacity of the streams, and we have a number of different industries in Pennsylvania, and we wanted to make sure that we protected the economic development of all industries by not using up all the assimilative capacity, making it available to everyone. We passed a new regulation last year that deals with TDS and requires this type of wastewater to be treated to a very stringent standard. Essentially, this type of wastewater has to meet the drinking water standard of 500 milligrams per liter before it's discharged to the stream. Air quality issues. We did two studies, one in the northeast, one in the southwest part of Pennsylvania, in 2010. Both of those studies came back. They found concentrations, as would be expected with the developing industry. They found concentrations of natural gas. They found elevated methane levels in the ambient air. But the conclusions were that they weren't levels that we needed to be concerned about yet. So that's the good news now, but again, we got to try to stay out ahead of this. They found some other pollutants, but as I just said, that's the good news is right now it's not something to be concerned about. We looked at other natural resources. I'm going to skip through this because this is a Nature Conservancy study. These slides are going to be available, so you can get on right there's a link to this Nature Conservancy study. This is not something done outside of DEP, so I just put it up here to let everyone know that we're looking, others are looking at this type of thing too, and we take it very seriously. Some key findings that were in that study. So in summary, those are the areas that this new industry touches on in Pennsylvania. Our department is addressing these as quickly and as well as we can, and we intend to continue to do so. And thanks.
Thanks very much, Dana. Next, very pleased to have Lynn, or Lyndon, full name, I just learned that, Pittenger, who has a 30 years experience as a petroleum engineer. He's currently a consultant. Before that, he had a long career with Unocal, as well as Occidental Oil and Gas in Houston. He does work across the country, but he was close enough that we were pleased to have him today. You know, part of this long-term prospect for natural gas as a fuel source is you know, as you heard, motivated partly by the price differential and what we hope is a fairly abundant supply. But I think we need to put that in context about that it's not going to be something that we just turn on overnight, and that's what Lynn's going to talk about. So please take it away.
So a significant change in policy can lead to a significant change in the demand for a product. And shale gas has been supplying, or is currently the main source of growth in the overall supply of gas of domestic resources in the country. Sometimes in the press it's referred to as a manufacturing process that's consistently repeatable across the extent of the play. I think that might be an optimistic representation. And for the last year and a half, I've been collaborating with Art Berman in articles in World Oil, as well as some of the blogs on that Art Berman writes. Been looking at the production data, publicly available production data from thousands of wells, looking at the ultimate recovery from these wells. And we come up with a bit of a different story in that the quality of these resources are quite variable. The core areas that perform well are a small fraction of the overall area of the plays. And some of the macro studies that have been projecting hundreds and thousands of TCF of shale gas potentially aren't taking into account the range and quality. This variation in quality is essentially going to lead to price sensitivity. There are parts of these plays that are commercially viable at current prices, but to get a full development, you're going to have to see a very dramatic change in the price environment of natural gas. Currently, the price of natural gas is at a historic discount to oil on an energy equivalent basis. On an energy equivalent basis, it's selling at a 75% discount. So what is shale gas? Typically the wells drill vertically 1 to 2.5 miles deep, and then drill a horizontal section about 4,000 to 10,000 feet long, and then fractured in a range of in a series of fracture stimulations where they isolate say zones of 200 to 400 feet of the wellbore. The staging allows the companies to focus the fracking energy on the shale formation and not the formations above and below, and also to get a more consistent amount of fracturing along the wellbore. What is new about shale gas? They've been drilling through the shale gas formations for over a century. It's been known that they're the source of gas. They always bled gas. The cuttings when they came to the surface showed that they were exuding some gas. It just wasn't recognized as a commercially producible formation. We've had the first horizontal well was drilled in 1929, but the real commercial application of horizontal wells took off in the 1980s. The fracture stimulations have been performed prior to 1950. The Mitchell company started drilling vertical wells in the Barnett Shale in the 1980s. The application of horizontal wells became started in the Barnett Shale in 2003, and within 2 or 3 years, many companies were competing for acreage in the area. It all of a sudden turned into the hottest play in the country. This graph is from the EIA 2000, I think it's updated recently, but from the EIA 2009 study. You can see that shale gas is the predominant source of growth in the overall natural gas production profile. They're currently about 24 BCF a year, TCF a year, and by 2035, be about 27 TCF a year, and that's about a 10% growth over that 26-year time frame. Shale gas, on the other hand, is contributing, is growing by 150%, and at the end, the exit rate in that graph is that it's producing 45% of the overall gas, and that the amount of shale gas produced from 2010 to 2035 is about 225 TCF. So that's just a number to keep in mind. I'll refer back to a few times in the presentation. Just some of the word slides. The Potential Gas Committee was developed out of the, I think, Colorado School of Mines. I don't know that much about it, but it's one of the better respected evaluations of natural gas resources in our future. It's updated about every 3 years. Their proved and probable estimate of natural gas is 441 TCF, with the shale gas contributing about 1/3 of that. And that volume that they estimated in 2009 is 147 TCF, and that compares to about 2/3 of the 225 TCF that the EIA has in their forecast. Now, that 2009 study had a dramatic increase in the amount of shale gas assumed, and it's very hard to see in the future. So the potential for these numbers to change in 5 or 10 years is quite substantial. So that disconnect, I'm not sure, is necessarily significant. This is a production profile or forecast of the shale gas, of the overall shale gas contribution to natural gas supply, based on the individual plays. And the reason why I show this is I want to show the impact of four of the key shale gas plays. The Barnett Shale is the oldest. That was developed with the vertical wells in the 1990s, converting to horizontal wells in 2003, and with the improvement in gas prices after 2003, became the hottest play in the shale gas. The next in a time frame is the Fayetteville in northern Arkansas, followed by the Haynesville, which is currently the most important source of growth in the shale gas. And potentially in this time frame, it looks like it's contributing about 1/3 of the overall shale gas profile. And then the Marcellus, which is currently rapidly growing, and because of its large areal extent, has potential for being a very important source. The collaborative work with Art Berman and I, looking at the publicly available data. This public data has monthly production volumes for each of the wells, or many of the wells in the plays, and they're searchable, so we can identify which production horizon they're come from, and the time they're drilled, and who operates the wells. The general findings after looking at several thousand wells in the Barnett is that Art and I estimate that the ultimate recovery of the wells are about 1.2, 1.3 BCF per well. Most operator presentations to investor presentations support, say, 2 to 2.5 BCF. In the Fayetteville, very similar findings, 1.2 BCF versus 2 to 2.5 BCF. In the Haynesville, we're seeing 2.5 BCF for the average of the wells. It's a much more problematic to estimate the ultimate recovery of the Haynesville because, one, there's not as much data, and two, the pressures, the wellhead flowing pressures are changing, and the public data doesn't have as much information on how those the surface flowing pressures are changing. So certainly there's a lot more uncertainty in that estimate. But we see a core area of 4.6 to 4.8 BCF per well, and the main operator in that core is 10 BCF per well. The Marcellus, unfortunately, the state does not require the publication of or making public the monthly production data. They do provide a cumulative cumulative production on a 6-month basis, and I'll show one graph on that. So we don't have any particular conclusions on the Marcellus, but the Marcellus is expected, many of the operators support a 4 to 4.5 BCF per well. In summary, the two main points of the presentation is our decline curve analysis tends to lead us to estimate the recovery of these wells to be about 50% or lower than what is generally discussed in the investor presentations. And then as important, the core areas where the wells are performing better are quite limited in extent, say 10 to 20% of the overall area of the plays. So I just want to go through quickly each of the key plays we're talking about. The Barnett data is substantial. We have 40, 50 months of data in some of the older wells, and we're seeing fairly established decline trends. This curve is the group average curves or these two curves represent about 450 wells and fairly established decline trends. And we're seeing a weighted average recovery of 1.2, 1.3 BCF per well, and that's based on the average, including 2,300 wells in that database. Fayetteville, 1.2 BCF per well for 2,000 wells. Once again, there's a lot of data and the fairly regular late time trends where we've got 20 to 30 months of data following a fairly established pattern. So it leads us to be fairly confident in these two trends. The Haynesville is much more difficult. It's a much higher pressure formation. It's actually initially at lithostatic pressure, which means that the gas is holding the fractures open at these initial conditions. And because of this extremely high pressure, and these are deep formations, the initial rates are very, very high, but the decline rates are very, very high. And we don't have as much data for this trend. And we also see very large pressure, flowing pressure, surface pressure changes, so it's much more challenging to evaluate this. But our estimates are about 2.5 BCF per well overall, with a core area of about 4.6 to 4.8 BCF, roughly half of the operator claims. This is an example of mapping of the core area where we see this, the black outline surrounds an area of about 160,000 acres, and the overall area of the Haynesville play is about 1.1 million acres in Louisiana and extends into Texas, including that acreage would be about 1.5 million acres. So here we have about 10% of the play in the core area where we're averaging 4.6 BCF. Now if we take that 160,000 acres and we assume somewhere between an eventual development spacing of 80 acres per well versus to 160 acres per well. So assume 120 acre average spacing per well. That'd give us 6.1 TCF out of the Haynesville core area. And the Haynesville is about 1/3 of the shale gas, and the shale gas is expected in the EIA estimate to produce 225 TCF in that 25-year time frame. So I think the extent of these core areas in these plays is very important. And then this is one piece of work that I thought might illustrate the price sensitivity of the resource. It shows the first 12, or the average of 44 wells with 12 months or more data, and the data points in the blue are the actual average of those 44 wells. And then we have a range of extrapolations, and this is the basis of most of the debate about the reserves of shale gas wells. Are these wells going to continually flatten and stabilize and produce over a 40, 50, 60-year time frame, or are they going to continue to decline at the similar rates that they are now and have a well life of about 10 to 15 years? Based on our work observing the Barnett shale wells and the Fayetteville, we think that we are not going to see as much flattening as is assumed by the operators. So we have some economics on the lower part of the page, where if you have more of the operator view of, say, 6.5 BCF per well, a higher IP and a flattening coefficient there, that you're commercial at about $4 or $5 per MCF, whereas much of the play is more in that $9, $10 range of being commercial. And then quickly, the data for the Marcellus play is in a different format, so it's hard, you can't analyze it like you can monthly production data. where we see a couple counties of outperformance. Susquehanna County is doing very well compared to the average 4.2 BCF type well that is supported by operators. Bradford County is also doing well. But there's a lot of activity in Washington and Greene County, and the data from those wells is underperforming the curve by a substantial fraction. And I'll skip this, but essentially the main point of the previous slide is that it's a highly competitive market, and you have to lease. The land gets leased up very quickly, and you have to drill on that acreage in the first 3 to 5 years to hold the acreage. Typically, 1 well per 640 acres. To get there, and much of the rate of drilling recently has been to hold acreage. The natural gas companies are also in a growth story that I think they're selling their shares of stock more on the momentum of a growth story rather than the overall chance of commerciality of running their business. The write-downs of the 5 key shale gas players totaled $37 billion in 2008 and 2009. And cash flow typically is about 150 to 300%. Capital investment to drill these wells is typically about 150 to 300% of cash flow from these companies. So you have the result is you have natural gas selling at historically low discount to oil and gas. There's a lot more activity drilling these wells than perhaps in a long-term basis can be justified. So, in conclusion, shale gas is not a manufacturing process, or best be considered not a manufacturing process. Quality and geology matters, and it's going to be sensitive to price. And overall, the shale gas supply may disappoint the EIA forecast by a factor of 2 to 4. Sorry for running over.
Okay, no, thanks very much. Thank you very much, Lynn. Finally, we have Dr. Stephen Hamburg, Chief Scientist with the Environmental Defense Fund. And Stephen started out as a forest ecologist with a PhD from Yale University and did his postdoc at Stanford, but he has done all kinds of climate-related work, has been recognized by EPA with an Environmental Merit Award for that work, and he is actually a lead author on the Intergovernmental Panel on Climate Change, which I think most of us in this room know about. And so obviously that's the perspective he's going to bring to this. We've heard the whole story from source to use, and very interested to hear what Stephen has to say about the climate GHG implications of that.
There we go. All right, thanks very much. And I'm going to be fairly brief, and what I want to do is build on what Callie said and what Daniel said, and dive a little bit deeper into the greenhouse gas implications of thinking about natural gas vehicles. And one of the key concepts that we need to address first is the issue of global warming potential and time. Historically, the IPCC has used 100 years to try and sort of come up with a standard global warming potential that can be compared across greenhouse gases, and that's what traditionally gets used in an analysis. But methane has some other characteristics because it's a relatively short-lived greenhouse gas, but it's a very potent greenhouse gas. It's really important to think about time in thinking about the greenhouse gas implications. So there's nothing magic about the exact years, but we have been thinking about it in terms of 20 years. So what are the net radiative forcing implications at a 20-year time step and a 100-year time step? And this really matters because if we just broadly, not speaking now into the specific topic today, put too much potent greenhouse gas in the atmosphere, we can lose the short-term battle to really negative effect because we are so heating up the atmosphere in the short term, even though we're on the trajectory to lower it later. So time matters. We can't just think about the 100-year global warming potential. We've got to think about the interim steps till we get to the 100 years. So we have to think. So we're using 20 years as the context to think about that. And I'm going to use this a different comparison, cold combustion and natural gas combustion, because there's better data about that. And we can think about the supply chain that Daniel referred to, and really what are the implications of greenhouse gas emissions across that supply chain. And there's data about that, and as Daniel talked about, they looked at that in the MIT study. And you can quantify that, and this is just some estimates that we have recently put together to try and understand those. Again, this is not the the case before us, but to give a context for it, again, I think the data is far stronger here. But even in this case, we do not have good error estimates. We do not have uncertainties around those two numbers on the right. And that's really what we need, because I could get into a longer discussion as the fact that the uncertainties associated with it, those are actually overlapping numbers. We cannot differentiate between them because of the uncertainties. That doesn't mean, in fact, they aren't different, but the data quality is not sufficient. And this is the theme that one of the key points that I want to bring out that's relevant to the issue before us today as well, is we really are lacking in good quantitative data in the natural gas leak rates throughout the processing, transformation, and use of natural gas. So that creates a lot of uncertainty in the implications, global warming potential implications of using natural gas. And these numbers, by the way, are with a 20-year estimate. So if we go and look at the literature, again, now comparing natural gas to coal, what we find is that the 20-year leak rate break-even point between those two fuels is between 4 and 6%. And the literature's got some fuzziness in it. There's even an issue in the literature now about what the appropriate global warming potential of 20 years is. There's some later data that suggests 72, which is the consensus right now, is probably too low, but we stuck with 72. But what we care about here is if we do it to gasoline, and I should have put gasoline diesel here because it's the same, that number from 4 to 6 goes to 1 or 2%. So if you have a leak rate of 1 or 2% over in the process of using it as a transportation fuel, you are going to be at the break-even point. And it's actually, in most cases, closer to the 1% than the 2%. But I put it as a range because I think that's a better representation of the uncertainty in the underlying analysis. But our data is not as strong as we'd like. There's really a lot of uncertainty here. And if we look at the 100-year, it's 3 to 5%. Those are very low numbers because, as Daniel said, EPA has raised their estimate to 2 to 2.5% upstream leakage. So that means, based on the best available data, which still has a lot of uncertainty, there's a lot of opportunity for refining those numbers. There's also opportunity that some of the uncertainty is that these numbers could be underestimates. The last revision was doubling the estimate. There's some other data to suggest it might be higher than the 2 and 2.5%. So what that says, going back, right, is that in the 20-year time frame, a natural gas vehicle is a net increase of net radiative forcing, meaning it's a negative relative to how much impact it's having on the global climate. It's not neutral, as Daniel says, in the 20-year time frame, most likely, best available data, there's lots of uncertainty, and I'm stressing that carefully because we are pushing really hard. We got to get better data to sort this out. We need more transparency with industry. We need to understand what the issues are. There is not good transparency across these data. And there's fights to even make it more transparent. That does not even include the actual use in the transportation sector itself. So what are the leak rates in CNG and LNG vehicles? There may be some data out there. It's not very visible. The data that we can find is limited, and it suggests that those numbers are considerably higher. So what we end up doing is, if we go back again to the 100-year global warming potential, which is probably what Daniel was referring to, we're now talking about neutral. It's going to be worse based on the data that we currently have in the short term, possibly break even in the longer term, but the error bars on it are too large. We shouldn't be making good public policy without better data and ensuring that we really get everyone working together, including industry, on all sides of this. Let's get the best data. Let's use the science to really answer this question, because right now there's too much uncertainty to really understand the implications. But the indications are, from a transportation fuel, we will, as the best data now, before we try and reduce the leak rates in the industry, we would actually be increasing net radiative forcing. Thank you.
Okay, so what you've heard from our presenters is a whole lot of information about what we called in the briefing known as challenges, right? There's a lot of potential benefits, but there are clearly challenges. And I think what we're going to try and do now is take a step back and see, which things are might be insurmountable, and which ones are manageable, and which ones are maybe not less significant than maybe we thought. And we've tried to piece this, we've brought together people who haven't probably been on a panel together to do this. But there is one organization that tries to wrestle with these issues and make the case and address these issues from a policy and a technical standpoint, and that's Natural Gas Vehicles for America, or NGV America, and Richard Koloje, their president, is here, and I just wanted to give him the opportunity to comment or maybe pose his top question from what he's heard from the panel today, and then we'll open it up to the floor.
We don't wrestle with those issues. We're advocates.
Okay.
I mean, we're objective, but we know what the objective is, which is to get more natural gas vehicles on the road. However, we try to deal with these things in an open way. Let me make a general statement, and I want to talk about some of the comments here. We have been fortunate. The entire Western civilization has been fortunate. For 100 years, we've had one fuel that was cheap and plentiful for all our transportation purposes. Our economies would not be near as robust if we didn't have that natural petroleum. It was cheap and it was plentiful. It is not plentiful anymore with respect to demand, and it's certainly not cheap anymore. And now we know other problems. We know about greenhouse gases. We know about urban pollution. We know about dependence on foreign oil and military sort of displacement, sort of distorting our military policy and distorting our foreign policy, and obviously shipping $300, $400 billion overseas every year sort of affects your job prospects. So we've had all that. So now we have to move away from that. The question is to what? And the answer is to everything. There is no one, anyone that tells you they have the answer for the transportation situation is lying. There is no single answer. We have to use everything that we have. Ethanol, natural gas, we have to use propane, we have to use electricity, and hybrid, all the technologies, all the fuels, if we're going to make a big impact on this. In the applications and in the parts of the economy, parts of the country, that make the most sense. And as you heard, the thing that makes the most sense for natural gas right now is high fuel use urban fleet vehicles, trash trucks, school buses, urban delivery vehicles of all types, over-the-road vehicles, et cetera, et cetera. The bigger vehicles, they use a lot of fuel. And that's what we're going after. Now, as you also heard, nothing's perfect. There's going to be trade-offs. There's environmental trade-offs. There's going to be issues of convenience, economics, et cetera, et cetera. But let me tell you, dealing with the public, there's environmental issues. There are dependence on foreign oil issues. No one cares. It's money. It's all about the cost. If you're not cheaper, they're not going to go with it. So we've got to figure out a way to make these things less expensive. Now, fortunately, natural gas is less expensive. Our vehicles are more expensive to buy, but less expensive to operate. And you've seen some of those numbers. You've heard those explanations. And so we're growing. Now, just a couple of points. On methanol, I've talked to Dan a number of times, trying to explain it to him. What he says is, with respect to methanol, what works in theory should work in practice. But with respect to LNG and natural gas, what works in practice shouldn't work in theory. Think about that. We've got 12.5 million natural gas vehicles on the road around the world. LNG, there's several thousand vehicles. It's growing. There is zero commercial methanol vehicles on the road. And that's the market speed. I think it's true to say that we're the fastest growing, natural gas, fastest growing alternative fuel vehicles in the world. Countries in Asia and Africa, South America, Europe, they're all growing. I love him dearly. I mean, he's got a great idea, and theoretically it makes a lot of sense, but it's not happening. In addition, the whole methane deal, the methane emissions in terms of what it means for greenhouse gases, you are absolutely right. There's no good data out there. But we have to move forward and to say, let's stop everything and let's wait till we analyze this, till we know what really is out there. You can't do that. We have to move forward. If we're going to display, or we can just do what we do now, use gasoline and diesel. All right, so,
I didn't actually say that.
Pardon?
I didn't say that.
No. I know, but no, I know you didn't say that. But
let the record show that he did not say that.
One of the problems So we have to move forward into something. By the way, natural gas, they keep talking about it as a bridge fuel, and we say, yeah, well, we don't know to where, and we don't know how long, but we can be a bridge to something. One of the things could be hydrogen. If you don't have a natural gas vehicle market, you're never going to make the jump to hydrogen. All the things that we're doing with natural gas, all the technology changes, the station changes, educating mechanics, inspectors, getting people familiar with gaseous fuels, all those things are setting the stage for hydrogen. I don't see how you make that jump to hydrogen, because we've done it with natural gas, and we have done it, and it has been painful. But now we're growing.
Rich, the bottom line is, I think the industry's happening, and a lot of these folks are in the business of trying to catch up with it, I guess, and I guess we all are. So if we could just let's finish up your point. I mean, we could. I'm not trying to cut you off, but just I want to be available for questions as well. So
on production, everything is dependent about technology. I mean, 15, 20 years ago, coal seam methane, nobody talked about that. Now, last year was 10% of the production of natural gas in the United States because of technology changes. You heard about the shale production. We've known about those shale formations forever. But technology changed, and suddenly the economics changed, and so we move forward. So all those numbers you saw up there, they're probably accurate numbers. I'll take your word for it. But those numbers could change very radically as the technology changes in terms of the price and demand. So I just want to make that point on
great.
production.
Thank you very much. And let's go ahead and let the panel respond, and then we'll take questions from the floor.
So one of the things I would respond to on the data issue is there is data out there, and it's not being shared by industry. So it's sort of, you can't have it both ways. So industry has got to be able to be transparent and share their leak rates within the whole supply chain. I'm not just talking about transportation, and the same with fleet managers. We need to get all of that data transparent, sort of in order to have the public compact of saying, look, we want to go forward with this. Let's share the data. Let's understand it.
I was under the impression that EPA has surveys right now that everybody is supposed to respond to.
They're supposed to. Right now the industry is actually trying to push back against that. In addition, there are opportunities to reduce emissions, and there's not a transparency. So the key is absolutely to support the EPA and have everyone proactively getting out there and really sharing data across the industry, and particularly in the transportation sector where the data is even least available.
But keep in mind, when you say pushing back is they don't want to reduce emissions.
No. They don't want to reveal their data.
But we're talking about leaking methane. Leaking methane is product you're throwing out the door. It's like shrinkage at a retail store. People stealing stuff.
But there's a lot of it.
But the industry doesn't want that. The industry would like to have zero leakage.
I'm sorry, just other responses from the panel. Those comments, I mean, not necessarily, if you have someone like to give you the opportunity, and then we can, go ahead, Dan.
And on Stephen's point about the greenhouse gas implications of using natural gas, there are two issues. One has to do with leak rates, which the EPA has estimated to be higher, and they've published some numbers. The second issue has to do with the global warming potential, and this is actually the larger effect. Now, the numbers you gave, Stephen, were for the 20-year global warming potential. But that is, so far at least, is not the established frame of reference by the IPCC or the EPA. I mean, this issue about the length of time over which the effect was to be taken into account has been discussed for a long time internationally. And the decision was, weighing all these factors, 100 years was more appropriate than 20 years. That makes a huge difference for natural gas, of course, because for 100 years, the number is 25. For 20 years, it's 72. So I think it's important to draw the distinctions. I mean, I think you're stretching things away from the accepted frame of reference when you talked about that frame of reference.
We won't get into the academic debate here, but I actually think that if you look at it, there's a growing movement away from the 100-year for the different gases because of the distortion it does on net radiative forcing, which is what we really care about. It was a convenience, I agree, but I think in fact that if you look at it now, it's probably not the norm and it's not the appropriate way to look at it from the end objective we've got. But we'll save this for a side.
Okay, I just want to, I can't help but, of course, respond to the comments Rich made about methanol. We've had this discussion for some time. I have to do it. Can't help it. Rich mentioned the importance of economics, and that's one reason I think methanol has such unique characteristics, because there's no doubt it can be produced at low cost as a liquid fuel, lower cost as a liquid fuel than gasoline or diesel. And that's really unique. I mean, what are the other alternatives for near-term liquid fuels that can be substituted for gasoline and diesel that actually cost less? In fact, most cost more. So the economics is a very attractive reason to think about it. With regard to no experience, in the late 1980s and early 1990s, over 15,000 vehicles were tested in the U.S., and the program was discontinued for a variety of reasons, one of which was that the interest in alternative fuels went down when oil prices collapsed. I did mention there are barriers, but on the other hand, everything involves weighing the pros and cons. And I tried to present in the case of methanol the concerns, but also I think it's very important to take into account this has this tremendous potential benefit if your goal is to reduce your dependence on foreign oil. It's a low-cost liquid fuel, and that is really unique. That's the point I'm trying to make.
Okay, questions from the floor. Sir,
Hi, yes, I'm wondering...
please identify yourself if you don't mind.
I'm Rob Warner from the Senate Commerce Committee, and I'm wondering how feasible is it to reduce the leakage rates that we have right now? I mean, do we have any idea how easy or expensive it might be to do this?
I don't know if there's anyone, I'm certainly not an expert on leak rates, but everything, in talking to people who are, I think it's very feasible, and that's one of the key benefits of trying to make transparent where those leak rates are. Because you do hear a lot about, well, you're throwing away product, but the bottom line is there is a lot of product getting thrown away. Some of that's probably inevitable, but at best I can understand from experts is, in fact, it's not all inevitable, and there are opportunities to reduce that leak rate. But we don't have a broad enough data set to really understand what the key variables are to that leak rate so we can hone in on where those opportunities exist.
Other questions? Gentleman in the back.
And you mentioned aversion of automobile and oil companies. I guess I can understand why there would be aversion of oil companies, but if the cost of converting a vehicle to methanol compatible is only $100 to $200, what are some of the aversions that the auto industry is not going to this?
Well, I can only speculate. I mean, the auto companies in general don't like to be required to spend any more money. I mean, they would not, even if methanol weren't part of the proposed open fuel standard, and where the standard was just that they should be required to produce a certain number of vehicles every year that would run on gasoline and ethanol, they wouldn't like to do it because it adds cost. And well, there is about $100 cost, extra cost, in going from gasoline to gasoline ethanol flex fuel vehicle. You have to have components that are more resistant to corrosion. If you want to go to methanol, it's another $100 to $200, and they don't like uncertainty. Well, what's their motivation to do it? But I think that's what it really. Everything comes down to, what is in the interest of a particular industry. And I don't see right now it's to the autos industry's self-interest to pursue this.
Gentleman in the third row.
One of the reasons, one of the issues with the auto makers is energy density issues that it creates for them as far as packaging vehicles. You're going to give up something, and that's becomes a real issue with consumers. So that's another version.
Yeah, that's true. That's another version. On the other hand, they're receptive to electric cars, which have very low energy density and very high costs. But apparently there's a motivation for them.
Sir in the side, then the gentleman in the back.
Before I go with the methanol, Stu, just a quick comment about methanol. Last year, there was a little over 2 billion gallons of methanol used as transportation fuel in China. That includes cars that are pulling up to regular gas stations and filling with 15% methanol in their vehicles. You have truck, taxi, and bus fleets running on M85 and neat methanol, M100. China determines that has made a determination that methanol is a strategic transportation fuel for the country, will help them reduce their dependence on imported oil. Some of the similarities here with the U.S., they have a lot of coal. They make a lot of methanol from coal gasification. We have a lot of coal. We just came back from a briefing this afternoon with the House Coal Caucus. We're talking about methanol from coal. Dan mentioned the Open Fuel Standard Act. We're expecting that bill to be reintroduced in the 112th Congress. Elliot Engel and John Simpkins will be the principal sponsors for that legislation. We'd be happy to talk to anybody here about the Open Fuel Standard Act.
Thank you. I want to get to the next question, but at some point maybe both methanol and natural gas in gaseous form, can come from other sources other than a shale formation. And I think you saw the CARB numbers from California about how the win-win just gets bigger over there. So at some point people might talk about the opportunity about that. But I'd like to get this gentleman in the back first.
Question, I guess, for relevant to both the first and second presentations. It's pretty noticeable that the vehicles which are most logically converted to compressed or liquefied natural gas are also fleet vehicles with lots of braking that benefit a lot from hybrid technology. It's also pretty noticeable that electricity looks better on your graph than natural gas vehicles in terms of greenhouse gas implications. And obviously a lot of the electric fleet in the U.S. is domestic fuel. So from a greenhouse gas and energy security point of view, why do I go with natural gas over electric or hybrid vehicles?
I would say because it's cheaper. And you mentioned that a lot of the fleets that do really well with natural gas are the ones that are like stopping and going quite a bit. And we're also advocates of combining different technologies also. I know UPS has a system of hydraulic braking where you can, air compression braking, when you're braking, you store up energy in compressed air and then release that for your next acceleration. And so really from the marketing side of things, we've got no problem with combining multiple technologies. I know that there are various issues on the cost of that and on, say, the packaging. But yeah, right now, I think, at least in those market segments you're talking about, CNG has a substantial cost advantage.
I'd like to also comment, but first I'd like to ask a question. Were you, in the alternative you were discussing, was it the hybrid vehicle as a way to get more efficient propulsion, or was it, did your comment also include plug-ins?
Because there are various studies that say the greenhouse implications of plug-ins are lower than current fleet vehicles. I think that's what we saw from the first.
Well, I have to be careful when you're looking at plug-ins because it depends where the electricity comes from. But I think the most important issue has to do with economics, which we discussed earlier. If you calculate the amount of greenhouse gas reduction ratio to the cost to society, that's a very low number for plug-ins because they're so expensive. So I think in discussing all these various options, there should be a common metric. You know, how much greenhouse gas reduction can you get for a given amount of money society spends? And then you wouldn't just have hybrids on there and plug-ins. You'd have more efficient gasoline engines. You'd have more efficient light-duty engines from clean diesel. You'd have CNG. But it should be done on a common basis. And I think actually that's what's missing in a lot of these discussions.
I'd like to just get Dana and Lynn in here. You know, I think you showed decline curves, and Dana talked about a lot of issues that they're really trying to get ahead of, as you say. But maybe I'd love you guys to talk about, I mean, the supply part of maybe, even though you shouldn't show the graph, there's a supply curve about that these, to maintain while existing conventional gas supplies are declining, we're trying to race to fill in that gap. And I guess I'm wondering if you guys have what you're thinking about in Pennsylvania, and Lynn more broadly about really just the intensity of gas development. Basically, are these things going to be, you know, we're at a certain development, pretty busy rate right now, a lot of activity in the industry, but is that going to have to basically escalate in terms of number of wells being drilled, frequency of drilling, all that other, and all the things that go along with that?
I can just speak to what we're seeing. I mean, we actually saw a very sharp increase from 2008 to 2009, but in 2010 it's kind of leveled off. Now, it could, in number of wells drilled and number of wells actually completed and producing now. We're not sure exactly whether that's related to the economics, the price of gas now, or whether it's related to other factors. But one thing that we don't think it's related to is the production. Because most of the wells that have been successful that you saw in the two counties are in Susquehanna and Bradford counties, where we're getting those highly productive wells. I think the focus now has shifted to that hot spot, if that's what you want to call it. But overall, the number of wells, new wells drilled, has leveled off.
Okay.
I think at these current natural gas prices, you have a lot of the natural gas companies are advertising a capital spending shift towards liquids-rich gas production or liquids, Bakken shale oil type plays, and the Eagle Ford shale. Every major player is advertising that's where they're going. EOG has made the switch much earlier than those players, trying to shift their liquid or their product mix much more towards the oily side than gas. So to me, I can't help but feel that this 75% discount to oil is temporary. It's not something you can plan for in the long term.
Okay, question over here, and one more, and then we got to wrap up there.
Hi, I'm not Morbid. I'm with NYH2O in New York City. Natural gas is a plethora of critical developmental hazards and facing regulatory problems, including disclosure of the hazardous waste chemicals used, which will surely put natural gas exemptions out of compliance with the Safe Drinking Water Act and Safe Air Act and the Superfund Act. Why would certain parties on this panel be proponents of investing billions of dollars, much of it subsidized governmental funds, in a short-lived, deleterious, cancer-causing procurement of a fossil fuel, which will ultimately be an obsolete energy source that creates much more irretrievable, critical, widespread damage than it solves, as compared to investing in sustainable energy, developed infrastructure? Shouldn't the focus be diverted away from this focus on natural gas because of the substantial external costs incurred, namely health, water filtration, land deterioration, to name a few? Why is the focus on natural gas so important, and why do any of you consider the cost, nearly the cost of the actual gallon or yes, the measure of gas to be the only cost that one considers when there are so many external costs involved, including Superfund restoration of land that has been irretrievably, the water has been irretrievably damaged?
I think we have the gist of the question. I guess I'm wondering if, Dana, you wouldn't mind, well, Callie wants to comment as well, but maybe she go first, but I wanted you to just comment on the exemption from this. There's some I think that I'm not sure if you guys deal with that at the state level, but there was a partial exemption for the fracking industry about the Safe Drinking Water Act.
I just have a very short reply, and you just really want to keep in mind that we're competing with diesel and gasoline. We're not competing with the ideal fuel that all of a sudden is going to propel all of our vehicles with no downsides. You know, there are very substantial downsides to both diesel and gasoline. So we believe that we're choosing, I don't want to say, we're choosing a better option by promoting natural gas and reducing the diesel or gasoline fuel use.
On costs that you have cited here, but certainly not the external costs that natural gas, that the procurement of natural gas involves, which is enormous on every level, resulting in health problems, water problems that are irretrievable in their aquifer decimation.
Yes, so does diesel and gas. A lot of it is not in our backyard, but
So,
you go to Ecuador,
Dana,
there's...
please comment on that, and also if you have any sentence about if for you guys to do your job right, if the cost, if there's a cost implication to the industry.
No, I mean, it's our job to prevent those deleterious effects, and that's what we're trying to get out ahead of with our regulatory revisions and our new construction standards. To date, we haven't seen, other than accidents, spills, industrial things that happen at any industrial site. We've seen those on occasion, truck accidents, those kinds of things, but we have not seen groundwater contamination. We have done an air study that shows that at the current, it is true, ma'am. There's no documentation that.
So, please, if you wouldn't mind, we're past our time, and I don't want to keep anyone. If there's, please feel free to excuse yourself. But there was a couple of questions on the floor, which I'll recognize, and then we'll wrap up.
Well, I'm Maddie Webster from Metro WMATA. We have a pretty big CNG bus fleet, as you all hopefully have ridden them and enjoyed them. Actually, my question did have to do with the cost benefit. And we have benefited tremendously from incentives for that fleet. But we now are doing some more serious evaluation of air quality impacts compared to other parts of our other drivetrain technologies in our fleet. And I would hope that when you all develop the policy that you can give us some more tools to make these decisions. I mean, I have heard repeatedly that the reason natural gas is the way to go, and I believe it too from my angle, is that it is very cost effective for us at this point in time. But I'm not sure that the cost benefit evaluation that you all are working on for policy direction is complete. That's all I'm suggesting. And further, you can help us make decisions better if we have more information.
Go ahead, Callie.
Okay. Actually, at INRO, we're just rolling out a vehicle life cycle cost calculator that's going to be available online. And actually, if you shoot me an email, I can send you the link to it. So that's just, yeah.
Go ahead, Stephen.
Just to the last two speakers, I want to say certainly I hope nobody took my comments as endorsing a technology, because I was actually not going either way. I think the key for all technologies, in this conversation we could be having across 6 different platforms, is about the transparency and ensuring that we have the data, that we have it effectively, that we have an open conversation about what it is. What I tried to present was exactly the way that I've been trying to approach it from a greenhouse gas, but it could go across the spectrum. And then we can have good policy if we make sure that we have that transparency.
Okay, I think that would be a great place to start, although I'm going to give our friend from United Parcel Service, who's actually wrestling with these issues on which way to go and electric versus, so please identify yourself and make a comment.
Yeah, I'm Jim Bruce. I was just going to respond to the question about why are we using natural gas as opposed to technologies like electric hybrid or hydraulic hybrid. UPS is fuel neutral in this. We have a rolling laboratory of about 1,900 vehicles in which we test everything. And the one vehicle that we have not been able to find an alternative fuel to diesel that met our environmental requirements, performance, and cost objectives was the heavy truck. And 18-wheelers are about a quarter of all commercial trucks 3/4 of the total fuel used by commercial trucks. And after 10 years of tests with 11 LNG heavy-duty trucks, 18-wheelers, we concluded that works. We just placed an order for 48 more. They are compliant with EPA 2010 requirements. And, that gives us now, that gives us a technology so that across the board of all of our vehicles, we either have efficiency measures like hydraulic hybrid, or we have alternative fuels themselves.
Okay, with that, we need to wrap up. I thank you very much for your patience, your indulgence in coming today. The presentations, video, audio recordings will be available on our website within 3 business days and www.esi.org. Thank you all very much, and let's give a big hand for our panel as well as yourselves.